Our next speaker hails from a very small town in the Texas Panhandle, where he was a state champion in the slide rule and a tuba player in the all-state band. And despite his plans to fly jet fighters, he accidentally enjoyed a career in the U.S. Air Force in materials research. And he retired to heaven at Rice University, working with a Nobel Prize winner who convinced him to try to save the world with nanotechnology. Please welcome Wade Adams.
Long walk across the stage to get the slide clicker. Thank you very much. I am from the Rice University and the Smalley Institute for Nanotechnology, as well as the Dean of Engineering's office now. So nanotechnology talks about things that are very small, but I worked for 3.5 years personally with a guy who had the most incredible big vision that I could ever imagine, and that has said here, we lead the world in solving humanity's most pressing problems through the application of nanotechnology. So in case you couldn't guess it, I am a technical optimist. So that person was Professor Rick Smalley, shown here with a couple of his students, who won the Nobel Prize, if you don't know what one looks like, there it is up there, for an 11-day project back in 1985 that was funded by the Army to do something entirely different. And in a period of 11 days, 3 professors and 2 students discovered a new molecule that nobody had ever imagined before. And that molecule is shown here. It's a carbon-60 molecule. This is a model of it, also known as Buckminster fullerene. That's the official chemical name, so it proves that scientists can have a sense of humor. And it's also known by its nickname, the buckyball. This upset the chemistry world terribly. They couldn't imagine a molecule like this, and it took the professors about 5 years of hard defense of the idea to convince them that they were right. It took somebody who could figure out how to manufacture enough of it so everybody could have a look at it to prove it was right. And this is one of the 3 seminal things that started the field of nanotechnology, and that was only in 1985. And the Nobel Prize came along about a decade later. So, nanotechnology hasn't been around very long. You may have read something about it in books and so forth in your earlier days. Is it molecular engineering, the Drexlerian idea of making atoms into little nano machines that look like machines and look like they do things that are typical of macroscopic devices? Or maybe you remember the Fantastic Voyage and the nanobots that are going to be injected into our veins, and they're going to go through and make repairs and solve all of our problems. That's just science fiction. The reality of what we're doing is even more interesting. Now, but we have to start with a few definitions. So I did work for the federal government for 37.5 years. At age 17, I was in the Air Force. And we all know the federal government does get things right. And this is their definition of nanotechnology. It's fairly wordy. You can read it at your leisure. It's got all kinds of cool words in it that are pretty exciting. But when you start actually thinking internationally and how you can define something in a simple matter, you come up with something like the application of scientific knowledge to the control and use of matter at the nanoscale where size-related phenomena do occur. A better definition came from one of our business workshops about a decade ago, the Rice Alliance. Anything is nanotech under the name of nanotechnology makes money. Much better working definition. So this is a good audience today, but you're not a tough audience. If you want a tough audience, go to the Ig Nobel Prize ceremony, which every year in Harvard that recognizes the worst science and engineering and all this other good stuff. And if you really want a tough assignment, get invited to give a 24/7 lecture. A 24/7 lecture at the Ig Nobel Prize ceremony is 24 seconds to describe the field, followed by a 7-word definition that your grandmother can understand. And about an hour before I went on stage, I came up with a definition. Talk about just-in-time thinking. And it seemed to me to be a very symmetric and good definition. Making small stuff do big things. That's the essence of nanotechnology. Let's get rid of this guy. Later, I realized I should add a couple more words to it, and then selling them. Because if you don't translate your science to the good of people, it's not really worth anything except a few papers and promotions in academia. By the way, let's take just a second. Here is a lawyer from New York with a V-chip card that if you go obscene in your discussion, he will stop you instantly. And here's the referee who times you, and at 24 seconds, you're kicked off the stage. So how big is nano? What is a nano? Well, nano is something of the order of 10 to the minus 9th meters. And to think in terms of 10 to the minus 9th or 10 to the plus 9th, divide it up into triple orders of magnitude. So a gigameter is about the size of the moon's orbit around the Earth. A megameter is about the distance from Houston to El Paso. Empire State Building is somewhere between a kilometer and a meter. Actually, with nano, we're talking about building kilometer-high buildings now. Dogs are a meter long, ants are a millimeter long. DNA is 10 to the minus 9th. Your bacteria in your blood cells are about a micrometer. So when you're working in nanometer size, you're way, 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 way smaller than things you can see, touch, feel, or have anything to do with as a naked human being. So that's not good, that's blank. Let's go forward. So those of you who have enough hair left to pluck one from your head, feel how thick a human hair is. It's about 100,000 nanometers thick. So when you're working with a nanometer, you're 100,000 times thinner than something you can feel with your hands. So here's the technical slide for today. This will be on the exam as you leave the room. And this is what makes nanotechnology exciting to people. So take a metal like gold. People know what gold is. They've got wearing rings that are gold and so forth. And you know what the properties are. It's shiny, it's a metal, it's hard. And but if you start chopping that gold metal particle up into smaller and smaller pieces, when you get down into the nanometer regime, you discover that its properties change. And for example, you can get size-dependent properties, and gold changes colors as it passes through smaller and smaller sizes, shown here by these solutions. So we're close to the basketball season coming up. Let's go Rockets. Basketball, here's one basketball, 23.8 centimeters in diameter, surface area of about 0.2 of a square meter. Let's chop that gold basketball up into smaller and smaller and smaller pieces until you get down to 25 nanometers diameter. You would discover you have 870 quintillion particles, and the surface area of all those particles is now 1.7 million meters squared. That's about the size of 4,000 basketball courts. So if you want to make a very sensitive detector, a sensor for something, or if you want to make an exquisitely powerful catalyst, if you make them nano-size, you take advantage of those size-dependent properties that you get. When you also get down to the nanometer scale, you get into interesting quantum effects, but we are not even going to talk about quantum mechanics here. You should be thankful for that. So here's a practical application that came out of Rice. The size-dependent properties of gold can be used to cure cancer. That's a subject of interest to a lot of people. So Professors Naomi Hallis, let's not do that yet, and Jennifer West, a professor of electrical engineering and a professor of bioengineering, came up with the idea that if you take a particle of sand that's somewhere between 20 and 60 nanometers in diameter, start coating it with nanoparticulate gold until it's a solid coating, it gives you a core shell structure like this. And as you change the diameter of the particle and as you change the thickness of the shell, you can change the color across the entire visible spectrum and push it into the infrared. And that's pretty cool, just by changing the size of the particle. And it can change the absorbance of the particle or the scattering of the particle with light. And why should a bio person be interested in that? Well, there's an interesting phenomena with tissue. So I've been using this green laser pointer. Everybody can see that pretty well. If I hold it up against my finger, it doesn't go through tissue at all. If, however, I take a red laser pointer, shown here, kind of harder to see, but now if I hold it up against my finger, it goes clear through. Infrared, it goes even farther. It goes up to 3 inches deep into the body. So if you can have a gold nanoshell that can selectively absorb that infrared radiation, you can deposit energy 3 inches deep in the body wherever you want it by putting a gold nanoshell there. So that was kind of an aha moment that was pretty cool. So here's the story. You take a gold nanoshell that's tailored appropriately. You put biomarkers on the nanoshell that are targeted to a particular cancer cell you'd like to go after. And this is the typical way of doing it, but it actually works well even if you don't do any targeting, because these gold nanoshells find their way to the leaky blood vessels in a tumor and selectively deposit themselves in the tumor. So then you inject them into the bloodstream, they circulate through, they find their cancer cells, you shine the infrared light through the tissue onto them. You can do a whole body shining, you don't feel a thing, and it heats up the cancer cells 10, 15 degrees, they die, and it's a pretty cool thing. Now, the problem is in animal testing on this, it worked so well that it became a financial and accounting nightmare because nobody had budgeted to keep the mice alive that long. Little Provost humor there. So here's the hind section of a mouse. Everybody recognizes that, of course. Here's an infrared laser beam going in, and there's 2 human breast cancer tumors that have been grown in the mouse specifically. And the only place that heats up is where the gold nanoshells have deposited into that tumor. So it worked. And the animal studies that have been done, here's the control group and the sham group that either got nothing or got nanoshells with no light. They all died within a month. The mice that were treated with this, 100% of them survived for certainly a year and a half after the treatment. So that was a pretty amazing phenomenon, and that led to the starting of Nanospectra Biosciences here in Houston. They're in phase 3 clinical trials for 2 initial cancers, but ultimately probably 40 different ones that are going to be tested. And the human results have been very good so far, but we're waiting on the very slow process for the government to get this approval. And it's a magnificent new way of treating cancer that's much better than the hammer that we use of treatment today with surgery and radiation and chemotherapy. So that's pretty cool. So this is a summary slide that I threw in to show you that that's one possible application. There are at least 200 different types of directions that nanotechnology is going in nanomedicine. And because the nanoparticles are very small, you can put a lot of them in the body. They have unique optical or magnetic properties. Sometimes you can use them for high strength. You can put multiple functions together at the same time for multiple types of treatments. They can be very bioresponsive, et cetera. It's a whole new world of medicine that's going on, and it's only about 10 years old that this has actually been being worked on. And so it's going to change the way we practice medicine from relatively few markers to go on, like for prostate cancer, for example, with very macroscopic, very coarse-grained diagnosis with a lot of surgery and radiation and so forth, and follow-up that's often late and at intervals that are awkward. Nano is going to make many, many, many more markers available. You can do this on a chip, and you can do a diagnosis of a heart attack in the ambulance on the way to the emergency room and get 100% reliability of the 80% of heart attacks that aren't really heart attacks. That can be done before you get to the emergency room, and you save the $10,000 charge for spending the night in the chest pain clinic. That happened to my wife, by the way, but she didn't have the advantage of the lab on a chip. So all these other things are important. One thing is that with nanotechnology, the large numbers we can use give you specificity with very small amounts. So instead of requiring 1 trillion markers to be detected to confirm a disease, with nanotechnology in principle, we can do it with zeptomolar amounts. That's 10 to the minus 21 moles. That's equal to 1 molecule. If there's 1 bad molecule in your body, with nanotechnology, we will be able to find that over the next decade or 2. Pretty amazing changes. So that's the nanomedicine part. Rick Smalley had 2 grand challenges, grand ideas about nanotechnology. One was nanomedicine, and that is proceeding here in Houston and elsewhere around the world at a horrendous pace, and it is going to change the face of medicine. It didn't happen quickly enough to save Rick Smalley's life, but it's going to save a lot of people. The other great vision was energy. So Rick Smalley got re-energized about energy about the time that I came to Rice, and he started going out and giving talks to small audiences, and he would put this chart up with nothing showing here for what the top 10 problems are. And he would ask the audience, shout out what you think are the top 10 problems facing humanity. We've heard of some of those today, and no audience that he ever talked to or that I ever talked to in those first 6 months or so ever mentioned energy before a fifth or sixth shout out. First time I gave a talk, one of my friends in the audience said, care for the elderly. We both had gray beards. That didn't make our top 10, but. So then Rick did a very incredible thing. He would take energy wherever it was on this list, which we'd fill in real time with PowerPoint, and he'd move energy up to the top and say, suppose a miracle happens, and we have all the energy we need on Earth, and it's widespread available, and it's cheap, and it's completely environmentally green. Can we solve the other problems on the list? And if you work your way down, we've already heard a lot about water. There's a lot of water on the planet, but it's got two problems. It's not where you want it to be, and it's got salt in it. You cannot solve those problems without energy. Food, C number 2, plus all the energy you consume producing and transporting, et cetera, food. Environment, a lot of our environmental problems come from the way we use energy, harvest energy, et cetera. Poverty is certainly definable as a lack of access to energy. Terrorism and war. Have we ever fought a war over energy lately? I can't think of any, actually. Disease, see bad water again. Education, you can't learn on an empty stomach, etc. So we may not be able to solve all of these problems, but if we don't have widespread available, cheap, and clean energy, it's going to be very hard to solve them. Is there any topic up here that you could move to the top and solve our problems as well? And there is one, and that's population. Let's move population to the top and invoke a different miracle and suppose when we hit 10 billion people by 2050, suppose 9 billion people just disappear. The Earth can easily sustain 1 billion people, but it's going to have a lot more trouble sustaining 10 billion. It's having trouble sustaining 7 billion right now. And nobody wants to invoke the miracle for number 10. So that meant the most important thing we could be working in nanotechnology for is energy. And so his vision was, in 2003, we consume about 14 terawatts of energy continuously. That's 210 million barrels of oil equivalent per day. 35% of that is oil. There's almost none of the rest of this that counts. By 2050, and you've heard that a bit today, we're going to need between 30 and 60 terawatts of energy, depending on how fast the world develops. That's equal to 450 to 900 million barrels of oil equivalent per day. That is an unbelievable number, and well over half of that is going to have to come from what we know as renewables. That's one reason why this administration has pushed to look far ahead, to start working on these problems and push the research to enable that to happen. We've had a basis of prosperity over the last century of oil. What's the basis of prosperity going to be for the rest of this century? Well, here's the way we use energy on the Earth today. This is a little extravagant, don't you think? There's 1, 2, 3, 4, 5, 6, 7, 8 250s on this sucker. Okay, it's a drug runner's boat. They needed that much power and speed, but think of how good a fishing boat this would be to get out and catch the big tuna in the Gulf of Mexico. Here's the way a lot of the rest of the world uses energy. It's a little weird, but the environmental question is, which of these last two scenes represents the worst environmental problem? And we've already heard a little bit about China. China has gone from bicycles to Buicks, and they're not my mother-in-law's Buick. Their Buicks already have to meet the CAFE standards that we've just been set for the next 15 years or so in this country. They're already using energy much more efficiently, but there's 1.3 billion of them or so. If they all get cars, where's the oil and gas going to go? Okay, so here's a summary of the problem we're facing. This shows the billions of barrels equivalent per year we're consuming up here. This is 2010 right here about. So we're up here about 7 billion barrels, several hundred billion barrels. And here's oil, here's gas, here's coal, here's hydro, here's fission, fusion, here's the renewables. When we get to 2050, we're going to be about 9 billion people. We're going to need this much energy. And even with all the natural gas that's being discovered in shale, that's less than 10% of the gas resources on Earth. So it's going to change this a little bit, but it's not going to move it more than maybe a third of a bar on this scale. And as you see, the consumption goes up, the actual amount of recoverable, affordable oil, gas, et cetera, is going to go down. So the trouble with this estimate is that it's very conservative, and the actual demand curve is likely to be something more like this. This level area here, this amount here, has to be filled in by the kinds of energy that we're not able to get very much out of today. So that's why when I was in the Air Force, every time we captured an alien, the first thing we asked them was, do you have oil and can we get it? Little joke, it must be late in the afternoon, you're not laughing that loud. My wife found the answer at one of the tabloids in the drugstore, though. The reason Bush wanted to go back to the moon was the 10-cent a gallon oil that he could get on the moon and ship back to us. That's probably not the right answer either. So here's an eye chart that you don't need to read, but these are the active areas of nano and energy that are being worked all around the world. In this chart issued out of Europe, fossil fuels are right down here. But since then, the energy companies in Houston have awakened to the opportunities of nanotechnology to help find more oil, get more oil, and do it cheaply. So here's a situation that inspires me to wear this tie, which came from the National Renewable Energy Lab, that the answer to our energy problems in the long run has got to be the sun. Here's the amount of energy we consume per year. Here's the amount of coal, the amount of natural gas, maybe a tiny bit bigger than that now. And here's the amount of oil. And here we have hydro and tide power. We have geothermal. We have biomass. We have, and finally, the sun. So the sun has to ultimately be the source of our energy for the long term, maybe not in the next 50 years, but certainly the 50 after that, and certainly over the next century after that. So that points us to having a long-range look at the solutions. We can solve our problems today if we just use today's solar cells and covered up my hometown in the Panhandle of Texas. That would provide enough electrical power to supply the whole country using today's solar cells. Nobody would care if we covered up the Panhandle of Texas, right? If you want to provide all the world's power, you cover up the bad part of Texas that's anything north of Houston, all of Oklahoma, Kansas, Colorado, New Mexico. So now you're into red state, blue state issues and so forth. And that's possible with today's technology. You could take the small rectangles and put them in all the continents, and you could provide all the energy we need on Earth today from the sun with today's technology. But there's a big problem with this idea, and that's called night. We had a great talk this morning about about batteries to store electrical power, and that's part of the answer. So Rick Smalley walked into the office one day and said, here's my vision for the future of energy on this planet. We need to build a distributed storage generation grid that's going to change our energy system from hauling mass around the Earth to pushing electrons around wires around the Earth. We need to rewire the world with a new conductor that's going to be able to power everybody. And we need to be able to ship power over 12 time zones efficiently. If you can ship it over 12 time zones, you don't need to worry about storage nearly so much. So you make it distributed so that you can have solar cells on your roof. You're going to have a Sears Roebuck battery that's perhaps invented at MIT. You're going to have a hybrid car that you can store energy in. You're going to produce energy and put it in the grid, and all of the big energy sources we have today are still going to be useful. But if we don't have the ability to transport much more power through our grid than we have today, it's never going to work. So we're going to do that with something called the single-wall carbon nanotube. The model is over there. That's shown right here. It's the big brother of the buckyball, and it is basically a roll of Texas chicken wire made of carbon, rolled up and capped with a buckyball on either end. And this molecule has some very interesting properties. It's the strongest material that we will ever have in the universe. Whoa, did I really say that? Well, Rick Smalley said it first, so credit him. And he's likely right. This molecule can be made into fibers that are going to help Burt Rutan build even lighter aircraft and spacecraft, because this is stronger than what we're using today. And some of these nanotubes can conduct electricity much better than much better than copper or silver or aluminum. In fact, a single nanotube molecule that's a nanometer in diameter will conduct 50 microamps of current. So if you make a fiber that's 20 microns in diameter, it'll carry 2,000 amps of current, and that's what a centimeter diameter copper wire carries on the grid today. We could carry hundreds of thousands of amperes and millions of amperes if we can rewire the grid with this new material. And we're working on it now. We can make the fiber. We can't separate the conducting parts of the nanotubes when we make them, but we're working on it at Rice. We've been working on it since Smalley envisioned this, and we're getting close. We're close enough that we're starting a company late this year. We think over the next 2 years we'll have the first demo models of this incredible wire. And it works at high temperature, low temperature, room temperature, any temperature. It's not as susceptible. It doesn't have to be cryo-cooled in order to give this conductivity. So this is a great vision. Without funding, it's just hallucination. Without hardware, it's just delusion. And the old adage is, actually a fairly new adage, money buys progress. We want progress in these areas. We have to put the money into the research to develop them. This shows how the American government has supported research over the last 50 years or so. We've gone from the age of space. This is the Apollo program here, which has dwindled a bit over the last 30 years or so. We've been through the age of medicine, which is still ongoing here. That's the big blue dot. If we're going into the age of energy, where energy is the most important problem facing humanity over the next 50 years, this little green bar here needs to be ramped up considerably because we need more basic research to make things happen that are going to help us solve the problem. And if we're going into the second age of space, where we're actually going to compete with the Chinese or do anything else ourselves in space, that yellow bar needs to be bigger too. That's my soapbox statement for today. So I'm calling for a massive new government funding program. This is supposed to get a little humor here, especially in the election time. And here's the reality that we're looking at. Easily accessible fossil fuel. Here we are today. Man, we're rolling in it. But not too many years from now, our children are going to be on the downslope and our grandchildren are going to be further down on the downslope. There's got to be some new stuff come along to help that work. So this is what I don't want to see. How about you spend less time studying how my generation destroyed the environment and more time figuring out a magical solution? I would never say magical solution. It's a nanotechnology solution. So what can you do? Learn as much as you can about energy. Be more informed about energy. Half of what you read is probably absolutely wrong. Learn as much as possible about nanotechnology because many answers to a lot of our technical problems are coming from nanotech. Encourage kids to study science and engineering. Start saving energy yourself. A negawatt is as important as a positive watt. If you can save a watt, that's as valuable as harvesting another watt from the earth. So the question is, will energy or space or nanomedicine motivate kids to go into science or engineering? We didn't talk about it, but if you've got the strongest material in the universe, you can build a space elevator. Here's Rick Smalley as a kid. He's very much a visionary. Doesn't he look like a visionary? Here's me as a kid. I'm just the troublemaker. But as Burt Rutan said, in 1958, when this book was published, and I was a sixth grader, I read the book, and that pushed me into wanting to go fly and want to be an astronaut. And I dedicated myself to going to fly. I went to the Air Force Academy. Didn't work out. I wasn't medically qualified. But it inspired me to stay in science and has been a very, very great career. And here's now who I care about. This is my first granddaughter. She's definitely class of 2030 at Rice, I think. I know that because she was in my office when she was 13 months old, and she was making these buckyball models. And soon she said, "All done, Grandpa, what's next?" Now, clearly that's Rice material. And we're passing it on to the second and third granddaughter now. So Millie's is leading the pack here. And I'll close with Rick Smalley's mantra we came up with as we were doing these things. Be a scientist, save the world, because we are equal opportunity employers. Be an engineer, save the world works also. Thank you very much. Now the exam comes.
I'll make the questions very short. But look, one thing is it seems extremely futuristic, and what I want to know is where is nanotechnology making a beachhead in the economy right now?
Well, if you look on the web, there's a website, which I can't remember the name, consumerproducts.org or something. There's over 2,000 products that are out there that are being used by people now with nanotechnology. There have been there are baseball bats with nano in them. There are sporting equipment is always the early adopters. Nano is in some of the race cars. Aviation is starting to pick up on it. Medicine is big time. There are hundreds of clinical trials going on now with nanotechnology-assisted therapies. You can measure, you can actually sequence your DNA with a nanopore by pulling it through a film, and it's sensitive enough to do the sequencing as it goes through the film, and you will be able to get your own genetic code very cheaply in the future, and that'll help your doctor diagnose what you're likely to get later and figure out a way to stop it. So those things are coming. Medicine is certainly within the next 5 years, there's going to be products approved. There's 2 or 3 approved right now. There's going to be a flood of them in the next decade and 2 decades. We're going to be really changing the face of medicine. Diagnosing that you have a disease that wouldn't be diagnosed by conventional methods for 15 years, you're going to get it at the very onset of it.
That's great. The future's very bright. And I want to let you know that I'm wearing my Nano cufflinks here. So I want to let you know firsthand that
I think you need a buckyball.
The technology is having an effect on the fashion world. So I want to let you know that.
So you now have a buckyball on your lapel.
Thank you so much for
Great.
this. Okay, thank you,
Thank you.
Dr. Adams.